Welcome to Brain Vision.
Okay, so in this problem, we have a string whose mu has a value of 1.60 grams per meter. And so that's the same as 0.00160 kilograms per meter. And then we're also told that it is held between two clamps at a length of 48.0 centimeters, which is, of course, 0.480 meters. And then we're told that it is put under tension that is variable over time. And it starts at 15 newtons and ends at 25 newtons, and it goes through that change linearly over 3.5 seconds. So we can write its tension as a function of time as 15.0 plus 10.0 t divided by 3.50. And then we are supposed to use this information to figure out how many oscillations the string completes as this tension is increasing from 15 to 25 newtons. Let's just dive right into the problem. So the first thing we need to do is we need to figure out, we need to get a formula for the frequency of the standing waves on this string. So that, of course, is going to be equal to, we're going to say that F is equal to V over lambda. We're told that this string is going to have nodes at either end, and it's just going to be in the first mode of vibration, the fundamental frequency. So we don't have to worry about higher end values or anything like that. And so the wavelength is going to be twice the length of the string, and because the string is put under tension and we're given the mu value and all of that, its velocity is just going to be equal to the square root of t over mu. So F is going to be equal to 1 over 2L times the square root of t divided by mu. Well, now we can we can substitute the equation that we have for t in to get a function of f over time. So f of time is going to be equal to 1 over 2L times the square root of, and the numerator we have, I'm going to kind of flip around the order to make it a little bit more intuitive, 10.0 t divided by 3.50 plus 15.0. And then in the denominator, we have, once again, mu. And so I'm going to rewrite this again to make it a little bit nicer. So we can separate the square root of the numerator and the denominator since mu is going to be constant, but t, of course, changes over time. So we can rewrite this as 1 over 2L square root mu. And then that's all multiplied by the square root of the tension formula. 10.0 t divided by 3.50 plus 15.0. All right, so that is our formula for f as a function of time. So frequency, of course, is cycles in units of cycles per section. Sorry, I can't talk. Frequency is, of course, in units of cycles per second. So the way that we can go from frequency to the total number of cycles completed over a length of time is we take a definite integral of the frequency from one time point to another. So we want to take an integral of our frequency equation. So in order to get the number of cycles, we'll say that n, capital N for number, is going to be the integral from 0 to 3.50 seconds of f of t dt, which then, of course, becomes, if we just expand the formula, the integral of from 0 to 3.5 of 1 over 2L square root mu times the square root of 10.0 t divided by 3.50. 3.50 plus 15.0 and dt. So what's nice about this is we already have a bunch of constants out to the front. So we can pull the 1/2 or 1 over 2L square root mu out of the integral because they're all constants, so we don't need to worry about that. But the equation under the square root does present a little bit of an issue. But it's not horrible. We can pretty easily solve this by doing some substitution. Or, the way I learned it, it was called U substitution, where you would set the kind of internal function to a variable called U. And then we'd evaluate du and help to kind of make things a little bit simpler. So we can say that underneath the radical, we can say that u is equal to 10.0 t over 3.50 plus 15.0. And that would make du equal to 10.0 divided by 3.50 times dt. So the way that we can do this is we'll go ahead and rewrite the integral. So n is equal to, and then we'll pull the constants out to the front. So 1 over 2L square root mu. And then we will have our integral. But because we've changed, because it's a definite integral and we're changing our variable, the limits of the integration are going to change too. We had the limits of integration in terms of time, but now we have to have it in terms of u, which happens to be also our tension force. So we'll just go ahead and plug in our formula for u here, we have, we'll plug in for t, 0 and 3.5. So at t equals 0, u is going to be equal to 15. So that'll be our lower limit of integration. And at t equals 3.5, our u will be equal to 25.0. And it just so happens that that is our tension at the beginning and the end of the time interval. Because u is the same formula as t, capital T. So then we're going to have, under the square root, since we're saying that u is equal to what it was under the square root, our integral now just becomes u, square root of u times du. But du is not equal to dt, so du is equal to 10 divided by 3.5 times dt. So to make the whole equation consistent, we have to then divide the whole equation by 10 divided by 3.5. In other words, we can just pull to the front 3.5, oops, it's kind of messy, 3.5 divided by 10. And so now this is a much easier thing to deal with because integrating the square root of u is much easier than integrating what we had before. So then the integral of u is then just, well, let's scroll down because we'll probably need a little bit more space. So we have that capital N is equal to 1 over 2L square root mu times 3.5 over 10. And then we have our integral, the evaluation of our integral. So the square root is the same thing as taking something to the 1/2 power. So in order to do the integral of that, we have to raise it and raise the power by 1 and then divide the whole thing by that power. So we'll be raising the power from 1/2 to 3/2 and then divide by 3/2, which is the same as multiplying as 2/3. So the integral of u, the square root of u, is equal to 2/3 u to the 3/2 power. And then that is going to be evaluated from 15 to 25. So the 2/3 can come out of the evaluation because it's going to be in, both apply it's going to multiply both the 25 and the 15 evaluation by 2/3. So we end up with n is equal to 1 over 2L divided by mu times 3.5 divided by 10 times 2/3 times, and then we have an open parentheses, we have 25.0 to the 3/2 minus 15.0 to the 3/2. And that is our final equation. We're getting to the end here. All we have to do is we have to plug in for L and mu. So n equals 1 over 2, and then L is 48 centimeters, or 0.480, and mu is going to be under square root. Mu is 0.00160. And that is multiplied by 3.5 divided by 10. That's multiplied by 2/3. And then we have in the parentheses 25.0 times 3 to the 3/2 power minus 15.0 to the 3/2 power. And you go ahead and plug all of that into your calculator, and you will get n is equal to 406, and then you'll get some decimal points after that. But those don't matter because we're talking about the number of oscillations that are completed. So we're just going to round down because the question specifically asks the number of completed oscillations, not how many of a fraction it gets to after that. So we'll just fully round down. So that means that our answer is n is equal to 406 oscillations. And that is how you do this problem.